All right, so today we're going to be diving deep into something that we all experience every single day, and that's gravity.
That's right.
You know, that thing that keeps your feet on the ground and makes sure your coffee doesn't float away.
Exactly.
But we're going to go beyond the basics today. So, even if you don't remember much from your high school physics class, don't worry. We're going to make it fun and pretty easy to understand.
Yeah, what's fascinating is gravity isn't just about things falling down. It's actually like the force that shapes entire galaxies. It dictates how planets move, and it even influences time itself.
Whoa, okay. So let's start with, like, the OG, the man who basically wrote the book on gravity, Isaac
Right.
Newton.
Of course.
Everyone's heard the Apple story, right?
Yeah.
But what does his universal law of gravitation actually tell us?
Well, it really comes down to this. Every single object in the universe attracts every other object.
Wait, hold on.
Yeah,
So you're telling me that I'm pulling on my phone right now and it's pulling back on me?
that's exactly right, yeah.
Okay, but then why aren't we all just, like, clumping together in one giant human blob?
Well, because the strength of gravity really depends on two major things: mass and distance. So the more massive an object is, the stronger its gravitational pull is going to be. And the closer the objects are, the stronger they attract each other.
Okay, so I get it. Since the Earth is way more massive than, say, my coffee mug,
Uh-huh.
its gravity wins the tug of war,
Yeah.
and my mug stays put on the table.
Exactly. And it's not just the Earth. The sun's massive gravity is what keeps all the planets in our solar system orbiting around it.
Right. Okay, that makes sense for things falling down or, like, staying in orbit. But what's keeping the planets from actually crashing into the sun?
Yeah.
Like, the sun's got this huge gravitational pull, right?
Right.
So shouldn't they just get sucked right in?
Well, that's where the idea of inertia comes into play. Imagine you throw a ball. It doesn't just drop straight down, right?
Right.
It travels forward for a while before gravity brings it back down to Earth.
Yeah. And the harder you throw it, the farther it goes before it hits the ground.
Exactly. Now imagine you could throw that ball so hard that it curved around the Earth instead of actually landing. That's basically what's happening with the planets. They're moving sideways so fast that even though the sun's gravity is pulling them in, their inertia keeps them in this curved path or orbit around the sun.
Oh, so it's like a delicate balance between the sun's pull and the planet's motion.
Yeah, like a cosmic dance, you could say.
Whoa.
Yeah.
And it's this balance that's responsible for, like, the whole structure of our solar system.
Exactly. It's why we have this beautiful organized system.
Wow. Okay, well, speaking of celestial objects, how does the moon fit into all of this? Because I know that it affects the tides, but how does gravity play into that?
Right. Well, it's all about the moon's gravitational pull on Earth. The side of the Earth that's facing the moon feels a stronger pull, and that pull is strong enough to actually tug on the oceans, causing this bulge of water or high tide.
Okay, that makes sense. But wait, isn't there a high tide on the opposite side of the Earth, too?
Right.
How does the moon's gravity cause that?
Yeah, that's where things get a bit counterintuitive. The moon's gravity is actually pulling the Earth itself a little bit,
Oh, okay.
slightly away from the water on the opposite side.
Gotcha.
So this creates another bulge, a second high tide, even though that side of Earth is farther away from the moon.
So it's almost like the moon is, like, stretching the Earth and its oceans,
Right.
creating two bulges of water on opposite sides.
Exactly.
Mind officially blown.
Yeah. And the sun's gravity also affects the tides, but the moon's effect is stronger because it's much closer to Earth.
Right.
So that's why we experience 2 high tides and 2 low tides every single day.
Whoa. This is making me realize that the moon does a lot more than just light up the night sky.
It does.
It's amazing.
And it's all thanks to gravity. It's this force that's constantly at work, shaping our universe in ways we often don't realize.
Right.
Okay, so before we move on to even more amazing things that gravity can do, let's quickly recap the basics. So far, we've learned that everything attracts everything else, thanks to gravity.
Yeah.
The strength of that attraction depends on mass and distance, and gravity is what keeps our feet on the ground, planets in orbit, and even influences the tides.
That's a great summary. And as we keep diving deeper into the world of gravity, you'll see that this fundamental force is even more fascinating and powerful than you can imagine.
Well, hold on to your hats, folks, because up next, we're going to explore some even more mind-blowing concepts like weightlessness in space and the mysterious world of black holes.
Welcome back. So before the break, we were talking about how the moon's gravity affects the Earth's tides.
Yeah, it's pretty wild how something so far away can have such a big impact, on our planet.
It is. That's the thing about gravity. It's a long-range force, it can act over huge distances, and as we learned, the strength really depends on both mass and distance.
Right. So the moon might not be as massive as the sun, but it's closer.
Right. Which is why it has a bigger influence on those times.
Exactly. But let's switch gears a bit and talk about something that's always fascinated people, and that's the idea of weightlessness in space.
Oh, yeah. The classic image of astronauts just floating effortlessly in their spaceships. But if gravity is everywhere, how is that even possible?
It's all about falling. Remember how we talked about planets? Like being in a constant state of falling towards the sun,
Uh-huh.
but missing because of their sideways motion?
Yeah, the whole cosmic dance thing.
Exactly. Well, astronauts in orbit are doing the same thing. They're falling towards Earth, but their spacecraft is moving forward at a really high speed. So this creates a constant state of free fall, which is what we experience as weightlessness.
So they're not actually floating, they're just falling forever.
Pretty much, yeah.
That's kind of terrifying and awesome at the same time.
Yeah, it is. Think about it. If you were in an elevator and suddenly started falling, you'd feel weightless for a second, wouldn't you?
I guess so. I don't know if I really want to test that out, though.
Well, astronauts are essentially experiencing that same thing, but continuously because they're constantly falling around the Earth. It's not that there's no gravity up there, it's that they're falling at the same rate as their surroundings.
Oh, okay, that's making a little bit more sense. So if I was like floating out in deep space, far, far away from any planets or stars, would I be truly weightless then?
Yeah, you would, because you'd be so far from any massive objects that the gravitational pull would be extremely weak. So you'd be in a perpetual state of free fall, just drifting through the cosmos.
That sounds exhilarating and also a little lonely, to be honest.
Yeah.
Okay, so let's talk about something a bit more, well, literally grounded.
Okay.
We've been talking about how gravity affects things on this huge scale,
Mm.
but what about its impact on our daily lives?
Right. Well, one of the most obvious ways we experience gravity is through our weight. Your weight is simply the force of Earth's gravity pulling on your body.
So if I stepped on a scale on the moon, I would weigh less, but I wouldn't actually be any smaller.
You got it. Your mass, which is like the amount of matter in your body, would stay the same. It's just the force of gravity that's different. Since the moon's gravity is weaker than Earth's, you'd weigh less on the moon, even though you're made up of the same amount of stuff.
So technically, it's not really accurate to say, I'm trying to lose weight. It's more like I'm trying to lose gravity.
That's a good way to think about it.
Yeah.
But seriously, gravity plays a key role in so many aspects of our lives. It's why things fall down when we drop them, why rivers flow downhill, even why it's easier to walk downhill than uphill.
I never really thought about it that way,
Yeah.
but it makes total sense.
Right.
Gravity is like literally shaping our world
It is.
and our experiences in it.
Yeah. And speaking of shaping, did you know that gravity's responsible for the fact that planets are round?
Really?
Hmm.
How does that work? I mean, it makes sense that things fall down because of gravity, but how does it make a whole planet spherical?
Well, it's all about the way gravity pulls things together. Gravity pulls equally in all directions from the center of a massive object. So over millions of years, as planets formed from dust and gas, gravity pulled all that material inward and smoothed out any bumps or irregularities,
Ah, okay.
eventually forming a sphere.
So it's like the universe's giant cosmic sculptor, constantly molding these planets into these perfect spheres.
I like that. That's a great way to put it. And it's not just planets, stars are also spherical for the same reason.
That's pretty amazing.
Oh, yeah.
Okay, well, we've covered a lot about gravity's influence on planets and our everyday lives. But now I kind of want to get into something a bit more mysterious and awe-inspiring. Let's talk about black holes.
All right. The ultimate gravitational powerhouses. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape.
Okay, I've heard that before, but honestly, it's hard to wrap my head around. If they're black, how do we even know they're there?
Yeah, that's a great question. We can't see black holes directly, but we can observe their effects on the matter around them. For example, astronomers can see stars orbiting around seemingly empty space. And by studying those orbits, they can figure out that there must be a massive, invisible object there, a black hole, that's exerting that pull.
So it's like detective work, using gravity as the clue.
Exactly.
But how can something be so massive and yet invisible?
Well, a black hole's gravity is so strong that it warps the fabric of space-time around it. This warping is so extreme that it creates a region called the event horizon, which is like a point of no return. Once something crosses the event horizon, it can never escape, not even light.
Whoa, that's pretty mind-blowing. So it's not that black holes are actually black, it's that they're so dense that their gravity traps everything, including the light that would allow us to see them.
You got it. And because nothing can escape from a black hole, we can't directly observe what's going on inside them. They remain one of the most mysterious and intriguing objects in the universe.
This is seriously making me rethink everything I thought I knew about gravity.
Yeah.
But we've got even more to cover, so stay tuned for part 3, where we'll explore some truly wild concepts like gravitational waves and the search for a unified theory of everything. All right, welcome back to the final part of our deep dive into gravity. We've talked about falling apples, orbiting planets, even those mind-boggling black holes. But guess what? There's still more to uncover.
That's right. Today we'll discuss something called gravitational waves.
Gravitational waves. Okay, that sounds kind of like something straight out of a sci-fi movie.
Well, it's real and it's amazing. Remember space-time? The stage where everything in the universe happens.
Yeah, it's not just where things are, but also when they are. Right.
Exactly.
Yeah.
Now imagine something incredibly massive, like two black holes spiraling towards each other, and eventually they collide. That kind of event would release a tremendous amount of energy, creating ripples that spread out through space-time itself, like waves spreading out from a pebble dropped in a pond.
So these gravitational waves, they're literally like distortions in the fabric of the universe.
That's it. It's like the universe itself is ringing, vibrating from these massive events.
Wow, but if space-time is like the very foundation of the universe, wouldn't these waves mess things up?
Well, the effects are usually tiny, especially by the time they get to us here on Earth. They cause a slight stretching and squeezing of space, but it's so subtle that it's incredibly difficult to detect.
So how do we even know they exist if they're so small?
It took some brilliant minds and incredible technology. Scientists built these super-sensitive detectors called interferometers. They use lasers and mirrors to measure those tiny changes in distance caused by passing gravitational waves.
Hold on, so we can actually measure these ripples in space-time. That's incredible.
We can, and actually the first gravitational waves were detected back in 2015, which confirmed Einstein's prediction from over a century ago. It was a huge moment in science because it opened up a whole new way of observing the universe.
Wow, so we can actually listen to the universe, hear these echoes of massive events happening millions of light years away.
You got it. Gravitational wave astronomy is a whole new field, letting us explore the universe in ways we never could before. We can learn about black holes, neutron stars, even the very early universe, just by studying these waves.
Okay, my mind is officially blown. We've gone from falling apples to ripples in space-time. Feels like we've covered so much. Is there anything else we need to know about gravity?
One of the biggest mysteries in physics is still how gravity fits in with all the other fundamental forces of nature. We've got the strong force, the weak force, the electromagnetic force, but gravity seems to play by its own rules.
It's like the rebel of the forces.
You could say that. Physicists dream of finding one theory, a really elegant one, that can explain all the forces, including gravity. That's what we call a unified theory of everything, or a theory of quantum gravity.
A theory of everything. That's a pretty ambitious goal. Are we even
That's the exciting part, we just don't know. There are some really promising ideas out there, like string theory and loop quantum gravity, but none have been fully proven yet. The search is ongoing, and it's one of the most fascinating areas in physics today.
This has been an incredible journey. I feel like I've learned so much, from the basics to the truly mind-boggling.
And remember, we've only scratched the surface. Gravity is a force that just keeps on fascinating and inspiring scientists and explorers.
It's amazing, right? Something so familiar that we experience every single day can also be so mysterious. Who knows what other secrets gravity holds, just waiting to be discovered.
Exactly. So next time you feel that pull of gravity, remember, you're experiencing one of the most fundamental forces in the universe. A force that shapes stars, planets, galaxies, even time itself.
That's a pretty amazing thought to end on. Thanks for joining us on this deep dive into the world of gravity. Until next time, keep looking up and keep wondering.